Okay, ladies and gentlemen, in the next problem, here we have a periodic signal x of n, which is equal to cosine of 6 pi over 13 n plus pi over 6, which is a discrete time periodic signal, and n goes from 0, 1, 2, 3, and consequently up to n minus 1. N minus 1, and here we are to determine the Fourier series coefficient the spectra of the signal and consequently the power spectrum. Now then, in the given signal, let us go to the solution. In the given signal or the provided signal, the fundamental period omega naught occurs as twice pi over n, which in this case is equal to 6 pi over 13. Now 6 pi over 13 can be written in the form of twice pi over 13 times 3. So this 3 is nothing but an integer multiple of the fundamental period omega naught. So this value is our required omega naught. Now if omega naught equals to twice pi over 13, from there we can get the period of the signal n to be equal to 13. Now let us go to the solution of the signal. X of n equal to cosine of 6 pi over 13 plus pi over 6. These can be written or expanded using the Euler's relationship, of course, equal to e to the power j 6 pi 13n plus pi over 6 plus e to the power minus j 6 pi over 13 times n plus pi over 6, which is wholly divided by half, rather than half, which is divided by 2. So upon further expansion, x of n becomes this term. Here is a constant. So we can write it as e to the power j pi by 6 over 2 e to the power j of 6 pi by 13 can be written as 3 times twice pi over 13 times n. This is done, of course, to compare it with the synthesis equation. The next term consequently becomes e to the power minus j pi over 6 divided by 2 times e to the power j of minus 3 times twice pi over 13 n. Hopefully up until now it is quite clear, and comparing it with the synthesis equation, with synthesis equation we get this value where k equals 3, c of 3 to be equal to e to the power j pi by 6 by 2, and c of minus 3 e to the power minus j pi by 6 over 2. These two are the required Fourier series coefficients. So one part of the problem is solved. Now, in order to determine the phase or magnitude spectrum, say for C of 3 can be written as half of this expression can be expanded using the Euler's relation as such: cos of pi by 6 plus j sine of pi by 6, which can be further written as half of cos of pi by 6 plus j by 2 sine of pi by 6. So the magnitude of C3 becomes root over 1/2 squared cos squared pi by 6 plus 1/2 squared sine squared pi by 6. So taking half as common and bringing it out of the square root operator, this becomes half, and all we remain with cos square pi by 6 plus sine squared pi by 6. Of course, from basic trigonometry, we note that cos square of alpha plus sine square of alpha is equal to 1. So half times 1 is equal to half. And consequently, the angle of C3 becomes tan inverse half the imaginary part sine of pi by 6 half cosine of pi by 6. This half and half cancels out, and all we remain with is tan inverse sine over cos is equal to tan pi by 6. And as per the rules of inverse trigonometric operator, this tan inverse and tan inverse will cancel out, and we'll get the angle to be pi by 6. Hope that is clear. Now let us operate for this second coefficient. So C of minus 3 is equal to e to the power minus j pi over 6 whole over 2 can be expanded as half cosine of pi over 6 minus j by 2 sine of pi over 6. So from here we can determine the magnitude to be equal to half squared cos squared pi by 6 half squared cos squared sine squared pi by 6, which we are to take the square root of. So as before, if we take 1 over 2 outside the square root operator, all we are left with is cos square pi by 6 plus sine squared pi by 6. Of course, this term will be equal to 1, so the magnitude is half. And the angle, the argument will be tan inverse negative half of sine pi by 6 half of cosine pi by 6, which is equal to pi by 6. Now upon plotting for the magnitude spectrum, this is magnitude of C of k, goes from k. So at the value 1, the C of k is 0, 2, 0, and 3, it will be half. Similarly, here it will be 1, 2, 3, negative 1 it will be 0, negative 2 it will also be 0, at negative 3 the value will be half. Similarly, there will be a negative sign over here. To determine the phase spectra, angle of C of k, where at 1 the angle is 0, 2 the angle is 0, 3 the angle will be pi over 6, 1, 2, 3, 0. At negative 1 it is 0, negative 2 it is also 0, at negative 3 it will be negative of pi by 6. So in order to determine the phase spectra, we only need is to make this value ck squared, and squaring this value will give 1 over 4, and here 1 over 4. So the phase spectra is at 3 and negative 3, the value is 1 over 4. This is C of k square, of course. So I hope you are able to determine the magnitude and phase spectra along with the power spectrum of this problem. The only difference is that when we get this sort of value, you can simply expand it as Euler's equation. I hope this problem is clear to you all.